Hello, good morning, everybody. We are here at Valeria's talk. Her full name is Valeria Gazzola. I hope I'm getting that right. And she is leading the Mechanisms of Social Behavior group and co-leading the Social Brain Lab at the Neuroscience Institute at the Netherlands Institute for Neurosciences in Amsterdam. She's also at the same time an associate professor at the University of Amsterdam. So starting in Dr. Zolati's lab with where mirror neurons were first discovered, she has since moved beyond motor mimicry and is now working on sensory and emotional mirror responses. Today, she will give us a talk about the neural basis of empathy from human and animal research. So we'll let her take away the talk. Just a reminder that you can ask her any questions during the talk using the Ask a Question button with plus or minus screen to indicate if you want to ask the question in person on screen. And otherwise, fire away with the talk.
Yeah, good morning, everyone. And thank you for the opportunity of being here online. It's quite of an interesting experience for me too. And thank you for the introductions as well. So now I would like to switch the time of the day and make you think we are in the evening instead of in the morning, and you're ready to go to bed. And suddenly a friend of yours is just sending a WhatsApp message with a picture like this one and saying that one of your best friends was caught in a fight later this afternoon. And now what would you do? Would you actually go and stay with him at the hospital? So the message was really trying to ask for, calling for someone to spend the night with him. Or would you, just continue staying on your couch and finish your book you were reading and fall asleep nicely? So what I'm interested in is in these kind of situations where there is a bit of conflict between your interests and the interests of other people. And I'm interested in understanding the brain mechanism, basically, that are involved in processing these kind of images and also helping or contributing to your decisions, whether you want to go or not. Of course, there are many things that can contribute to the decision, and I will not present you an overview of that. What I will concentrate is on some of the mechanisms we believe are part of this, of informing the decision making. And as I started my research in Rizzolati's lab, where the mirror neurons have been recorded, of course, I will also try to understand whether mirror kind of responses could contribute as well to the perception of these images and our decision making. So years of research, like I would say now about 20 years, have shown that if you ask somebody to come into the scanner and perform an action, you can easily map basically the circuit that is involved in this doing an action. And of course, as we all know, we would expect the premotor, somatosensory, and cortices to be there, cerebellum included. And then we would then ask our participants to instead watch somebody else performing similar actions. And in this way, you can again map the circuits involved in observing somebody's actions. And you can see whether there is an overlap between the two, which is the white clusters that you see here. And indeed, what you see is that most of the circuit involved in observing somebody else's actions overlap with the circuits involved in you performing the actions yourself. And since the mirror neurons as well, there is basically this idea that when we observe somebody else's performing an action, we basically activate our own motor repertoire or the motor machinery that we would use to perform the action ourselves, giving us a quite intuitive first understanding of what goes on in the other. So when you would see the picture of your friend here, you would activate all these premotor and somatosensory cortex of both your friend and the bad guy too, right? You just activate everything that relates to the action. And as I mentioned, these two areas in particular are considered the homologues of the regions in which mirror neurons have been recorded. So we know that in these neurons, it is likely, also in humans, that there will be actual neurons that respond to both. Of course, in humans, it's difficult to show. So we need to take it carefully, but this is a bit the idea. And similar processes have been shown to happen for sensation. For instance, if you are touched, and you come to the scanner, I can map your somatosensory regions very nicely. And now if I ask you to observe somebody else being touched, I can look for the overlap again. And we know that part of the somatosensory cortices will be reactivated by these observations. So again, when you see this image of your friend, together with all the motor responses you get at with the motor circuit, you would also have part of the sensation, how it feels to be grabbed that way and probably to fall on the floor as well. And the same with emotions. So if I put you in the scanner, I let you smell very bad odorants like rotten eggs, I can map your insula very nicely, and I can see that part of this insula will be also active when you see somebody else being discussed. So same things also for pain. If I slap you on the hand here, or if I ask you to observe somebody being slapped or being receiving a painful action, you will see again an overlap both in the insula and in this case of the anterior cingulate cortex. So again, here there is not just actions and sensation involved, but also the emotion behind how your friend probably feels like. And then it means that together with the somatosensory part of the premotor, you would also probably have part of your insula and the anterior cingulate cortex activated. So this is a very brief overview of the last 20 years of research, but it was just to give you a bit the idea of the state of the art at this point, where when we see pictures of this type, or also real events, or when we hear sounds, that happen in these situations, basically you don't only activate vision or audition, but you also activate the premotor and motor machinery and the somatosensory cortices and cortices associated with experiences of emotions and when yourself. And all this activation basically would bring up what we call a vicarious state, the state instead of the other. So what the other is feeling, a first perception of what goes on into the other. And this would give us, this very first intuition and really makes it more real what happens to the other, because you sort of feel it yourself. Of course, you need to be very critical when I'm saying all of this to you, because what I've been showing mostly to you so far were correlations, right? We see the brain activity going up whenever you see these kind of images, right? And they go up and down, up and down. So my idea of the vicarious state to give you a perception of what goes on in the other is a bit fragile, because to really say that do participate in perception, I need to show that these regions are sort of necessary to you for you to perceive. And the way we started to look for causality, basically, and the necessity of these areas was by combining TMS and fMRI, and TMS and behavior. And here is just one example of an experiment in which we did presented actions of other people, but in this case, we also added a task. And the task was to let us know which of these two boxes was the heaviest. So if we now take the circuit that we know it's activated during the action observation, we would expect, for instance, the somatosensory cortex to contribute to this perception of weight. And we would expect that if we go and stimulate with TMS the somatosensory cortex, then I should basically perturb your ability to judge properly the weight. And this is indeed what we found when we compared a fake simulation with the real simulation. Basically, you see that participants become worse in estimating the weight of these objects from observing other people's actions. And Antonian Hamilton before us did a similar experiment where she stimulated instead the premotor cortex, the ventral part of it, and again showed that if you stimulate this node, you have a reduction in task performance when you need to judge the weight. And we also had the opportunity to collaborate with patients that had a spinal cerebellar ataxia, which is a disease that affects the Purkinje cells of the cerebellum. And what we observed there as well is that patients that have basically not well-functioning cerebellum are also worse in judging this task. And the cerebellum was always one of the nodes of the circuits as well. So basically, if you put all these studies together, what they show is that when you have a circuit involved in seeing, for instance, these actions of your friend, all of these nodes seems to contribute somehow to your perception of that image, because perturbing any of them basically perturbs your perception. And what we know from an additional experiment is that whenever you perturb, for instance, a region like the somatosensory, this perturbation is also reflected in changes in activity in the other regions that are connected to it. So it really shows that the circuit is really a circuit. And if you basically perturb one region, you're actually perturbing the whole circuit. And you need this joint activity basically in order to perceive correctly the actions. So, of course, it would be nice to show that also the insula and the anterior cingulate cortex are kind of necessary for the perceptions of the emotions. And unfortunately, as you probably know, it is very hard to stimulate these regions with the tools that we have nowadays available for humans. They're not precise enough or deep enough to really go and selectively stimulate the anterior insula. So we relied on works done in patients again. And basically what has been shown is that if you have a damage in the anterior insula, you would not anymore go always for the chocolate cake instead of the molded one, but you would be happy to accept this very rotten piece of cake. It would be really, okay, it's another piece of cake for you. And the same, if you have damage over the anterior insula, you would no longer be able to accurately recognize disgusted faces when presented to them. So we have some evidence here as well that the activity of the anterior insula, for instance, is necessary, or at least in part is necessary for your correct perception of this. Basically, I hope that now I was a bit stronger in convincing you that basically this vicarious state, or the fact that we reactivate the regions of involved in sensations and action and emotion when you observe somebody else, that they contribute to perception, because when I perturb them, my perception is also perturbed. Again, it might not be the only way in which we perceive. I will never stop conveying this message, but of course, these reactivations do contribute to perception. So now, if you think about pain, for instance, when we hurt ourselves, right? I'm slamming the door and my finger stays in the door. It's quite painful, right? So the fact that I feel pain basically serves as a motivator for me to remove the cause of the pain, or not to leave my fingers in the door anymore, right? So the idea here was, okay, could it be that the reactivations of areas that are involved in my own first experience of an emotion, for instance, or a sensation of pain, serve as a motivator to basically go and help somebody else in pain? So would these reactivations serve as a motivator for prosocial behavior? So would they help? So reactivating all these areas when you see these pictures would make you go and spend the night with your friend. I see a lot of questions on this guest. Maybe I look about them late. It's kind of difficult not to be distracted by the question. It's fun. Okay, so the way we try to investigate whether this vicarious activity could serve a bit as a motivator was by asking participants to come in the scanner again, or in the experimental room, and watch these kind of movies where somebody, so you basically come in pairs. One of you will be the pain receiver, and the other one will be the one in which either we record the activities from or we perturb the activity. And then the actual participants will basically see the pain receiver confederate getting an electroshock. And now the participants will have a choice. So I give you €6, and you can decide whether you want to keep all these €6 or you want to donate part of these euros to reduce then the strength of the next stimulation. So if you now saw the first movie and you say, oh, it's not very painful, right? So I'm not going to donate anything. Then what you will see next is another movie that shows a similar intensity of the electrical shock. On the other hand, if you donated €5 because you thought it was very painful, then the next video will show basically a very mild shock that is not painful. And what you observe behaviorally is a very nice correlation as expected. So the task worked between the donations, how much people donated, and the intensity of the first video that was shown. So higher is the intensity and more people donate. And the idea, the perfect experiment would be now to go with TMS and stimulate the insula. And as I told you before, this is not really easily possible in humans. So we opted to stimulate the somatosensory cortex. Why? First of all, it's nicely on top of the head, so you can really reach it with the TMS. And second, we also know from other experiments that the somatosensory is also activated by pain, but when you see basically the source of the pain. So when the pain is conveyed by where you are hurt, like in these movies, where it is the hand that is, you see, moving as a consequence of the slap. And here in the face was only the face conveying the pain, while the pain was delivered on the hand and the hand was not moving. We would expect that if we have now, if we compare these type of stimuli, then the somatosensory should be activated by the hand type of stimulus and less from the face. And then we could perturb basically the somatosensory regions and see what happens in the task. So we did observe indeed that the somatosensory was responsive to the hand videos and also actually to the face videos. But then when we went to stimulate during the first video with the TMS, the somatosensory cortex, what we observed is that the nice relationship that we observed before between the donation and the intensity of the pain stimulus was not so nice anymore. So people, there was not anymore a clear relationship between the observed pain and how much money people would donate. And this, though, was only true for the hand. And indeed, what we stimulated was the hand representation of in the somatosensory cortex. So if you see the difference between the sham and the active for the hand is significantly different from the difference that is not there, basically, for the face. So the question at this point was a bit, okay, is this stimulation, is the contribution of the somatosensory having an effect directly into the decision to whether donate or not? Or the decision is perturbed because with the stimulation, we perturb the way we perceived the stimulus to start with. And so to address this question, what we did, we basically had a second experiment in which instead of asking to donate money, we simply asked the people to tell us how much pain they perceived in these videos, right? And if we do that, while we excite the somatosensory cortex with TDCS, in this case, we see that we are able to change this relationship, and in this case, to improve it, again, only for the hand. And the fact that we were able to change the activity, basically the rating or this relationship during the rating task with the TDCS suggests that basically what happened in the helping task, in the donation task, is that your perception when we stimulate the somatosensory is not accurate anymore. And this as a consequence, probably on the decision making, because the information that goes into the decision making is not clear anymore. And that's why you don't have such a nice and clear relationship anymore. So basically, to summarize, the idea is that you see the pain of other people in a way or the other, right? And now I just show the face. But this elicits this vicarious state, which will help you to attribute now a value to the pain of the other. And now it will be very easy to attribute this value because basically you bring the pain of the other through this reactivation into your own machinery. So now you know how it feels in a way to be heard. And this value will feed into decision making, where of course you have all of the other variables of the situation coming into play. and then at the end you will decide whether to help or not. And if we perturb this perception, basically, the value might be altered, and as a consequence, the decision making, and finally, the action, or not, because the action actually depends also by this computation as well. But now let's try to think of interesting cases, right? How can we challenge these? So what is happening here? Now you are a famous boxer and you are in your final game. So what is really happening here? There is a lot of violence and there is also a lot of money. So one option could be that people that go to these sports are less sensitive to the pain of others. So a bit similar to the perturbation example. So you have a perturbed or a different state to start with. Or it could be that you simply, what is at stake, it's quite different from the first example I gave you. So simply this situation enters directly into the decision making. Or maybe there is, I don't know, a switch somewhere or something that can regulate everything, even how much we perceive or not. So these are some of the possibilities. And so we were very interested in trying to understand, and we are very interested in understanding how this works and this variability works. So one very old experiment we did was with a group of incarcerated people they committed crimes, so they were considered psychopaths. And we asked them to watch videos of somebody being hurt or somebody being like rejected. So it's moral kind of inclusion, and neutral, like neutral interaction, or nice interaction, like having a caress. And then in the scanner, again, we hurt them. So we had this ruler, we slapped them, or we pushed them away when they were looking for the experimental hand. And everyone reported really to feel excluded somehow. Or to have neutral interaction, like shaking the hands or being caressed by the experimenter. And then what we observed in the control group is, as expected, and as I was telling you from the beginning, we had basically a combination of regions involved in motor perception, like the premotor and the somatosensory. So also the sensation that is induced by these videos, and the emotions that are conveyed here. So the insula and the anterior cingulate cortex. And then the idea was that psychopath, so that's also how we started a little bit the experiment. The idea was that they would have a reduced response to the stimuli to start with. And when we basically now show the voxels that were activated both by the experience and the observation of the stimuli I just showed you, you see that indeed the psychopathic individuals have a reduced activity in these regions. And you see it even better here, where the controls, all these regions, the premotor, somatosensory, insula, are more strongly activated by the control. So at first we were, very kind of, this fits very nicely with our idea. Indeed, they have reduced activity, and this is why they are less sensitive to the pain of the other. But then we thought, okay, you also hear stories from people around that say, but he was such a nice guy. You know, it was such a nice father. How can he be such a bad guy? How could he murder his wife? I mean, it's impossible. I cannot believe that. So if somebody is so able to charm somebody else, right, it should have some abilities not to show in other occasions some level of empathy. So if he really has such a level responses to the state of the other, he would never probably be able to synchronize so nicely to the other, or to give such an impression of being a good guy. So we asked them as a follow-up to really try to empathize with the receiving hand. So the hand that was receiving the pain or the caress. So we only selected these two types of movies. And now we looked for their brain activity again. And when we do this, we see that basically the differences between the control group and the incarcerated people are not there anymore. So that suggests that they were actually able to empathize if they needed to. So when we asked them to empathize, they were perfectly fine, and all these activities were actually there. Suggesting again that what was maybe the problem there was not a lack of ability of being able to empathize, but maybe they don't have such a spontaneity to do so, or maybe they need a reason to do so. And this suggests that indeed people might be equipped basically with regulatory mechanism. And not only them have this regulatory mechanism, but everyone, and they might be better at it, for instance. And indeed, when we ask people to watch movies, either under the instruction to empathize with the character in the movies or to be detached, right? To look at a bit of as an experimenter, then we see that the brain regions in the premotor regions, somatosensory regions, they synchronize more between individuals when they are asked to empathize with the character in the movies compared to when they asked to detach, suggesting indeed that this regulatory mechanism is there for everyone. And then we would need, as a future experiment, maybe to understand whether indeed people with psychopathy are maybe better at regulating, or they have a more complex regulation system, or with some, or deficitarian. I don't know, right? But it could be really the difference relies in how they regulate empathy, basically. So all this part of the human work, I always enjoy running it. And I also, at the same time, get a bit frustrated by it. Because, as I mentioned at the beginning, I'm very interested in the brain mechanism that help regulating empathy, or that they help forming empathy, or all these kind of aspects. And unfortunately, fMRI, TMS, EEG are very useful tools, but they have big limitations in terms of looking, for instance, at single cell responses or a more detailed mechanism. And this is why in the lab, we always have been pushing a combination of human and animal work in order to really extend what we can, be inspired from the human work, and to really look it in a more mechanistic way. So what I'm now what I want to show you is a bit of the work that we have been starting in the animal as well. So in order to, of course, move from human to animals, in particular to rodents, we need to understand a little bit better what we mean when we speak about empathy. Because, of course, empathy can be seen as a very complex term, and not everyone would agree that animals have empathy. And now I will explain you also why. So here I have a bit of illustrations. So I see empathy as a tree. And what I would put as the roots of empathy are basically phenomena like emotional contagion and mimicry. So things where you are affected by the emotions of the other without the need of you being aware that the emotion is of the other. Like when you're a baby and one starts crying, so everyone cries. When we are at the stadium looking at a game and we start cheering, you don't need to think about the fact that you feel happy also because you feel contagious by the other. You are just contagious. And then what we see is empathy proper, where many would say that it also requires your awareness, the awareness that the emotions that you're sharing is felt by somebody else, and you are just sharing the emotion, but it's not necessarily your own emotion. And then we have concepts like sympathy, where you go a little bit further, you feel the emotions of the other, and now you also feel warm feelings towards the other person, right? Where you can understand what the other person also goes. And then we have prosocial behavior that could serve at times as a measure of processes like empathy. So what can we actually measure in rodents? So I would say that in empathy, unfortunately, cannot be directly measured, because we cannot measure whether the rat is aware or not in what's going on. It doesn't mean that it's not aware, but we can't measure it, so we can't conclude anything. Sympathy is the same thing.
And then emotional contagion, on the other hand, I think we can measure. And I will show you a couple of paradigms that do that. Oh, sorry. And prosocial behavior, again, it has some problems in whether we want to really call it prosocial behavior because it has to be intentional or not. But maybe it's something that it can also, to a certain level, be measured. So the classical task we use, so after in the rats is the following. So after an initial habituation phase, we go into the test phase. So you have two rats put together. One we refer to as the observer, the other as the demonstrator. A bit like in the helping task I show you in the humans. So the observer will watch the demonstrator receive a shock. In this case, there are 5 short shocks. And what we measure is basically the response to this shock, which is freezing. So the animal that is shocked will first, of course, be a bit shocked, react like, oops, what's going on? And then it will freeze because he's afraid, he's scared of this pain. And if we measure now here the amount of freezing during baseline, you see that there is no freezing going on. And then in orange red, we see the demonstrator behavior. And you see that so during the first shock, there is not immediate freezing. But then from the second shock onwards, it freezes basically 80 to 90% of the time. And if we look now at the behavior of the observer, we see that at the beginning, there is not much freezing, but towards the end, it starts to be a little bit of freezing, not as much as the demonstrator, but a little bit. But now, if we introduce a pre-exposure phase, sorry, in between the habituation and the test, in which the observer experiences some shocks, and then it's going to the test session where the observer will only watch the demonstrator receiving the shock. Now, if we measure freezing, you see how nicely these two curves overlap. So if the observer knows what a shock means, you will see that he will freeze as much as the demonstrator, just by using as a cue the fact the demonstrator freezes and the behavior of the demonstrator. So here I had a movie, let's see, so for you to take a look. So here they are just exploring. So this is the baseline. They show a very normal behavior. And now you see the shock, the demonstrator here. So he moves. At first it's like, oh, what's going on? I don't want to have that. And now I didn't stop the movie, right? They are both freezing. And you see the demonstrator moves and the observer still freezes. Look. So this is what basically we would observe in this kind of task, where we see that the observer is affected, and more so when it knows what the experience is, by what goes on into the other. And this is what we would call emotional contagion. And now what we can do in the animal is to do electrophysiology and really see whether we can find cells in the observer that respond both to the experience of pain and to the observation of pain. And because between the insula and the anterior cingulate cortex that the human literature suggests, the anterior cingulate is the one that is more preserved across the species, we decided to start by recording in the anterior cingulate cortex. So here we got the silicon probes, and we made the rat experience heat, laser heat, because of course the electrical shock would screw up the implant. So we would look for another form of pain, which is a heat laser. And you see the responses, how nicely they go up to the heat, and it much more so than in a low laser condition. And then here we are plotting the responses, the cell responses to the observation of shock. And again, you see a nice, how nicely the signal goes up to the observation of it. And here you see the single cell response, and this is of course the average of the cells. And it responds more to the high shock compared to the low shock. And then because pain includes both the sensation of pain, but also the fear of, the anticipation of pain and the fact that you don't want to get pain, we decided to introduce a third condition. So basically during the pre-exposure, we now also present a sound. So we have a normal fear conditioning paradigm for the observer. And when we play back the sound in the third condition, basically we see that there is a very little response, almost not, to the fear, suggesting that the response was more reflecting the pain component rather than the fear component. And here indeed, if we would go and count the number of cells responding to the observation in green, those to the experience of pain in red, and those responding to fear in blue, you will see that there is a big overlap between the self-experience and the observation of pain. And there is also some overlap between the observation and the experience of fear, but a very small number overlaps for all three conditions. So suggesting a certain degree of specificity and diversity between the cells. This because I think I'm going a little bit over time, and I want to show you your last two experiments. So here we also were able to disrupt the activity in the anterior cingulate, and here we do it with mucimol, which is a GABA agonist, and in the future we're going to be much more precise and hopefully only inhibit the mirror neurons, but let's leave it for the future. And when we inject mucimol, we see that in the observer, we see that when there is saline, so no mucimol, the freezing is basically normal, 80%. But for the animals in which we injected mucimol, there is a reduction in the behavior. And this is not the case during the conditioning, so during the fear. And what you see here, interesting enough, if we now measure what's happening to the demo, we see that the demonstrator that were paired with animal with saline freeze as much as usual. But demonstrator that were paired with animals that had mucimol, they also freeze less, suggesting that the information flows does not only go in one direction, but it actually goes in both directions. And we do indeed observe this in the past. We always observe that basically demonstrator that were paired with animal that experienced the shock ahead with the observer that the experience before, they all froze more than the demonstrator that they were paired with the animals that did not receive the pre-exposure. You know, and if you remember the first graphs I showed you, you also saw that the observer without the pre-exposure, they froze less compared to the demonstrator. And if you try to explain the signal, for instance, of the observer by only including the past, what happens in the past, and in this case is amount of freezing, right? So we can explain the current freezing as a combination of how much it froze in the past plus some error, or we can express the current amount of freezing as a combination of how much the observer froze in the past plus how much the demonstrator froze in the past. Then we see that the combination of the function where we include the amount of freezing of both the witness and the demonstrator better describes the data. And the same is also true the other way around. When we try to describe the behavior, the amount of freezing of the demonstrator with just the past of the demonstrator, this will be worse in predicting the data, in describing the data, that when we include both the past of the demonstrator and the past of the witness. And this is the last experiment, which it's quite recent, and I'm really happy about it. So we have basically two rats. We teach one rat to press a lever, and one lever delivers 2 pellets, and the other one only 1. So of course, he will develop a preference for the one of the 2 pellets. And now what we are going to do is basically to associate a shock to the other whenever the rat presses the preferred lever, the orange one here. And we want to see whether this shock is enough to motivate the rat basically to switch between the preferred lever to the less preferred lever. And indeed, here you see at baseline, they preferred the red lever, and the moment in which we introduce the shock, this preference decreases. Okay, so they do switch when we associate the preferred lever to the shock, and this was independent of the sex of the animal. This was not true if no shock was delivered, and also if the shock was dissociated in time with the press of the lever. So if it's not anymore a consequence of your pressing, then there is no switch. And this was also true for unfamiliar victim. And it was not the case, though, if you increase the cost. So if the preferred lever was delivering 3 pellets instead of 2, then they will not switch. Again, suggesting that similar decision or complexity in decision with cost and benefits happens also in the case of animal. Of course, we don't know whether it's very much aware, but you know, this cost-benefits relationship holds for them too. And the same is true in the variability of the behavior of the animals. And in here, the full dots are those that switched, and here you have the one that did not switch. So they also present variability in the behavior, which we hope we can use to then investigate further a bit psychopathy-like kind of behavior.
Sorry, Valeria, we would have to wrap up really soon.
Exactly, that's the last slide. Okay. Indeed, if we perturb the ACC, again, basically they don't switch anymore. So to wrap up, the idea is what we are trying to do in the lab is to really investigate the mechanism of this, of the role of this vicarious activity in behavior. So we have this vicarious state. It can serve perception. It can serve adaptive to basically the inform the decision-making system, and to basically develop adaptive behavior. And of course, it can be regulated by situations and inter-individual differences. I would like to thank you, everyone. Sorry for being a bit longer than I expected to be. And these are the people that need a big thank for the experiments I've been showing in during the presentation. And this is basically our lab at the moment. I'm ready for the question.
Okay, thank you very much, Valeria, for the talk. It's fascinating. It definitely paints a fuller picture with the human and animal research for the empathy field. So we have actually many questions, but not really much time. We'll try to answer as many as we can. The first question, the most upvoted question, is actually coming from me. A rather general question, like what would be the evolutionary advantage to have empathy at all? And do you see a distribution of empathy levels in the lab in animals or humans? Would there be an optimal level of such empathy behavior?
Okay, okay. So I think that I start from the last one. So there is a lot of variability, and variability, I think, is necessary for adapting at the different situations. So I don't think that empathy is a construct where it's either there or not there. I think I don't embrace this view anymore. Maybe in the past I was grown up, you know, with either, oh, you're empathic or you're not empathic. I don't think so. I think that we are differently empathic in different contexts. And maybe there is also a genetic component where there is variability to start with and different susceptibility. So I really embrace also Zaki's view that empathy is something that you can learn, that you can adapt. Evolutionary, I mean, if you think of emotional contagion as one of the roots of empathy, it could simply be that is a fear that is a detection of the danger in the environment. So basically you use other individuals to perceive whether the environment is safe or not. So if you see that one individual is a bit scared, maybe you don't worry too much. But if you start seeing that more individuals are scared, then it might tell you something about the danger of that environment. So it is important that you are susceptible, or that you can perceive a little bit the state of the other in order to consider an environment safe or not. And we ran a couple of simulations for that, and we have some evidence, I would say, that it really could be the case, that you really use it as a fear detection in a way.
Okay, interesting. And then the second question is from Charleson, and they do not want to come on the screen, so I'll ask the question. Is there synaptic connectivity between mirror neurons from different brain regions? And how are they established, by learning or during brain development?
This is a great question. I love it, and this is what we are running at the moment. So we just hired a postdoc to actually try to address that because we don't know what kind of inputs they receive. We don't know at what part of the
the cortex or subcortical, they already start to emerge. And I'm looking forward to the answer, but I cannot give you an answer yet.
Well, keep posted for the last publication in a few years.
Yes, exactly.
Okay, we actually have time for one last question. It's from the other moderator, Varsha, today. And the question is, did the response of incarcerated members depend on the severity of the crime they had committed?
Okay, I'm not, honestly, I don't remember we looked at it, and I'm not even sure we could look at it because we really chose a cutoff that was above 27. So you have a scale that measures psychopathy, and we really took the highest in the scale. So I would say that they were quite homogeneous in that regard. So I'm not even sure we have enough variability to look to correlate the scale with the severity, basically, with the data. So I don't have an answer for that. It would be nice to so there sometimes you use the other scales in the normal population, that measure your psychopathy tendencies or characters. But again, the results are a bit not consistent so much. So it's we don't really have an answer yet.
Okay. Would you plan to look into that?
Yeah, I am interested in looking to that. What I'm trying to, so we have a collaboration now with the child psychiatry department. And so what we hope for is more looking at how teenagers learn the association, learn that hurting somebody else, it's not a good thing. So I'm more now, more than looking at the severity, I'm looking at how the process of how we learn to avoid hurting other changes in these kids, in these groups, because of course in kids there is the dissociation. There's basically you can be violent in two ways, right? It can just be a responsive kind of act of violence. So you're violent to me, or I'm very upset, and then I respond. So these are the reactive kids.
Mm-hmm.
Or you have a more premeditative act, right?
Mm-hmm.
And in this case, it's more the callous kind of kids, and they really it's much more premeditated, constructed. And so there is a bit the belief that these two group of kids, they behave differently while they grow, with one of the two groups more likely to persist and remain in the aggressive kind of behavior, and maybe developing more likely psychopathy than the other group that is more like impulsive and needs to just learn to regulate it, maybe with age. So there are a bit of these ideas around, and I'm trying to see whether indeed we can differentiate them, or we can.
Very interesting indeed. We'll have to wrap up here now, but I think the topic of empathy is particularly important nowadays when everyone in the society is under such pressure, and mental health is another hot topic. So if you guys are more interested in this topic, you can definitely visit Valeria's website and her research further on the internet. Okay, well, thank you very much for the session, and thank you, Valeria, for the wonderful talk. We'll see each other soon.
Thank you. Have a nice day.
Ciao.